Hi. In this tutorial, we're going to learn how to add toolpaths to a part. What is a toolpath, you ask? Well, if the tool were to travel along the drawn lines in your shape, it would result in an undersized part, and the holes would be too large. In order for the CNC machine to cut your shape accurately, it must travel along a path that is offset from the actual part drawing. When we add a toolpath, ToolShop calculates the optimum path for the tool to travel in order to achieve the desired dimensions. And it allows you to do much more than that. We will use the flange part that was created a couple of lessons ago for this purpose. Here we have a simple part that is made up of a single external parent shape and 5 child or internal shapes. Remember, we use the combine function in the transform menu to link them all into a single part. I would like to cut this part out of aluminum for this exercise. First, I need to make sure I have the correct material and thickness selected. I can see this up here on the toolbar. If you didn't select the correct material at the start of the job, you can easily change the current sheet by clicking on the Material Library button to the left of the current sheet, then selecting the material you wish to use for the job. In this case, I'm going to select 10 millimeter thick aluminum. Next, I will select the part. You should verify that the holes turn red when you select the part to make sure the combine has been done previously. If not, then you should combine them now. Next, we will go to the Toolpath toolbar. For this part, we will use the Offset toolpath. Offset is the normal type of toolpath that will be used for cutting out parts. Once the Offset toolpath window pops up, we need to select an appropriate tool. In this case, I'm going to choose the 6 millimeter router cutter. If you remember, we created a default toolpath for each tool when we added them to the tool changer setup. ToolShop will display all the tools that are suitable for this process and material. In this case, we only have a default toolpath template, which is available for use in all materials and all thicknesses. The default template is probably not the best setting for this material, so we will make a new template just for this material. Clicking on the New Template button opens up this small dialog box, which allows you to specify which material this new toolpath template will be applicable to. I will also give this template a practical name that will help me identify it later. We will choose the 6 millimeter router tool. I'm going to apply it to aluminum specifically, but I'm not going to restrict it to any specific thickness. I'll explain why in a moment. Next, let's give the template name. Let's call it aluminum/cut through and click OK. Now we have a blank template to specify the parameters that will be used for cutting this part. The great thing is that we are creating a template that can be used over and over and can be tweaked if required. I did cover some of these settings in an earlier tutorial, but I'm going to go through them again and explain how they relate to this situation. When ToolShop creates the new template, it will give you a summary at the top which tells you the tool position, the tool name, which material and thickness it will apply to. In this case, it will apply to all thicknesses, and the name that we called the template. You should also see the same template name in the list on the left. I'm going to make sure the cut width matches the diameter of the router bit. If we were using a laser, plasma, or water jet, then you would enter the cut width from the user manual for the selected consumables. Next, we have the depth parameters, which I'll expand by clicking on the small arrow here. Depth settings are not visible when using 2D tools, such as a laser or plasma, but for a router, the depth is very important. Notice there is a selection for relative location. Because I want this toolpath template to be usable for all thicknesses, I'm going to set the depth relative to below bottom. So no matter what the thickness is, it will adjust the depth of cut automatically to cut the specified depth below the bottom of the material. Entering 0.5 millimeters, or around 20 thousandths of an inch, will ensure the cutter goes all the way through the material and just a little into the sacrificial spoil board for a clean cut through. Next, I'm going to specify an XY feed rate of 4,500 millimeters per minute. I know from experience that this tool will cut at this speed. If you're unsure, then you can refer to the cutter manufacturer for their recommendations. I know this cutter can plunge quite well, so I'll enter AZ axis feed rate of 1,500 millimeters per minute. I don't need a dwell at the bottom of the plunge, so I'll specify 0 seconds for that. A dwell is more important for plasma and laser cutting. Because this is a fairly small tool, I'm going to use a high spindle speed of 20,000 revolutions per minute. You can enter whatever is appropriate for your cutting tool. I'm going to leave the overcut/undercut setting at 0 for now. If I wanted the cutter to overcut a little past the beginning as it is finishing the shape, then I would put a positive value here. For some thermal cutting processes, it may be useful to have a slight undercut, in which case we would enter a negative value. This is entirely up to you as the user. Next, we have the ramped lead-in setting. Because aluminum tends to bog up the cutter, let's select yes for this template. This will cause the machine to ramp down over the length of the specified lead-in, which we will set later. The next setting affects the cut direction. Selecting conventional cutting will cut anti-clockwise around the outside of shapes and clockwise inside holes. This method keeps the part on the left of the cutter when viewed from the direction of travel. Conventional cutting is usually suitable for most materials. However, if you have material that can melt under heat and pressure, then conventional cutting can sometimes leave swarf melted to the edge of the part. In this case, it may be preferable to select climb milling, which will cut with the part on the right side of the cutter path. Finally, we have the sharp corners setting. Normally, this is set to yes. Setting it to no will cause the tool path to follow a radius around any sharp corners. The next section is for tool pathing open contours. This section controls the behavior when you have any open shapes drawn in your parts. These are lines that do not join up, such as a fold line or similar. Setting Apply Toolpath to open contours will enable you to control whether the cutter will travel on the left, right, or down the center of the open contour. You can also turn collinear lead-ins on or off. This will cause the cutter to ramp down along the line towards one end, then reverse and cut the entire line at the set depth. Setting Apply Toolpath to open contours to no will completely ignore any open lines in your drawing. The next section is lead-in and lead-out. A lead-in is a small line or arc that extends out from the tool path at the entry point. Adding lead-ins reduces damage to the part when the cutter is piercing or plunging through the material. It is very important for processes like plasma cutting because it will damage the part if it pierces on the path. It is also important to have a lead-in when cutting plastic with a router because the cutter tends to heat up and cause a small divot in the side of the part. Using a lead-in avoids this problem. Selecting None will disable this feature. Selecting a straight lead-in will create a small entry line with the specified length and angle relative to the main toolpath. The arc lead-in is very useful for cutting holes with a plasma cutter, as it gives good thermal distribution and leaves the hole more circular. It can be used as you wish for other cutting processes. When routing aluminum, I like to use a follow-the-side lead-in. This will create a path that starts outside the shape and gradually comes into the path at a specified angle. The follow-the-side lead-in style will even work around curves and corners and is very useful when you don't want to leave large gaps between parts in a nest. I'll choose this style now. I'll set the length at 10 millimeters and the angle at 5 degrees, so we'll gradually move into the cutting path at a slight angle. Remember that we chose ramped lead-ins earlier, so the cutter will start cutting at the surface and gradually plunge down to the cutting depth along the length of the lead-in. Lead-out is the same, but at the end of the cut. We won't use this for now. The next section is pre-piercing. I'll skip over this for now, but it enables you to use a different tool to plunge through the material at the start point. This can be very useful on advanced plasma cutting machines that are fitted with a drill spindle. You could use this function to pierce through the material with a drill, then come back and start cutting on the edge of the drilled hole with a plasma torch. Multi-pass settings are only applicable to routers, milling cutters, and drills. These settings are extremely useful for the type of job we have here, because the cutter is unlikely to be able to cut all the way through in one go. I could manually say, I want to do this cutting in 2 passes by entering 2 in a number of passes box. But I want this template to be usable for all thicknesses of aluminum, so I'm going to use some more advanced techniques here. Firstly, I'll set the maximum depth per pass at a comfortable setting. I know from experience that my cutter can easily cut 6 millimeters deep per pass, so I'll set this at 6 millimeters. Notice that ToolShop has automatically selected 2 passes because this is how many are required to cut through the 10 millimeters material. Because I will have the maximum depth per pass saved in the template, it will automatically adjust the number of passes for each material thickness. Next, I'm going to change the ramping settings. I don't want the cutter to lift up and down for each path, so I'm not going to select separate passes. To save time, I'm going to set it to ramp down from pass to pass. This means it will cut at a set depth, and when it gets back around to the start of the first pass, it will then start ramping down to the next pass depth before continuing at that new depth. The ramping angle controls the angle of descent when it ramps down. This setting is not applicable to the other methods. The final method I could have chosen is continuous ramping. This literally spirals down around the part in a continuous manner until it reaches the full depth of cut. This is also a very useful method of ramping and gives consistent results. For now, I'm going to leave it set to ramp down from pass to pass. Notice there's a setting for use a cleanup pass. For this exercise, I'm going to turn this on. It is not always needed, but it can give excellent results if you require a mirror finish on your cuts. Using a cleanup pass can also increase your precision as it reduces the load on the cutter when doing the final cut. The cleanup offset actually modifies the first cuts by stepping them out a very small amount. Then it creates an extra final pass that cuts precisely at the correct offset to achieve the best tolerances and cut finish. You may find that 0.5 millimeters or 0.02 inch is suitable, but you can adjust this to achieve the best results. Cleanup pass thickness is the amount of material left in the bottom of the cut that the final cleanup path must remove. This can often be set to 0.5 millimeters or 0.02 inch. The remove bridges setting controls whether the final cleanup pass obeys any bridges or tabs, or if it cuts through them to remove them. The next section is starting depth. This is a time-saving setting and is useful for very deep cutting, such as in mold making. For example, you may have already pocketed out a large section of material, and perhaps you want to do some cutting in the bottom of the existing pocket. Instead of having the cutter cut in the air all the way down from the surface, you can get it to jump down to a height just above the bottom of the pocket and start cutting from there. It will still obey the multi-pass settings from that point on. I'm going to turn the cleanup pass off for this job. The next section is called miscellaneous settings. In the offset toolpath, we simply have the place bridges at regular intervals setting. This allows you to place bridges or tabs at a certain distance around the perimeter of shapes. You can choose the interval between bridges, as well as the ramping angle, length, and height for 3D bridges, or you can specify 2D bridges which are more suitable for plasma, water jet, and laser cutting. 2D bridges simply stop the cut and restart again after the bridge. I'm going to turn bridges off for now. The final section in the offset toolpath settings is for inlays. This allows you to create shapes in one material that fit perfectly into the rebate on a different material. This could be useful for inlaying some metal lettering into a timber panel, for instance. The inlay radius should be equal to or greater than the radius of your cutter. The gap creates a slight tolerance between the insert and the rebate in the panel. We won't need this function for now. Clicking OK will ask you if you want to save the new template for later use. Selecting Yes will then generate the toolpath for the selected shapes. Note that you can apply toolpaths to a whole sheet of parts at the same time. You can see that ToolShop has added the toolpath to the part. This is the actual path the cutter will follow. If you look closely, you can see the follow the side lead-ins coming in at 5 degrees. Next, I'm going to place my mouse pointer in the center of my part and click and hold the center button. This is the orbit function, which lets you look at things in 3 dimensions. Dragging the mouse around will move the viewport around the object. Can you see how ToolShop has created the 2 passes for the router bit? If the material was thicker, our adaptive toolpath would have automatically generated the correct number of passes to achieve the full cut depth. We hope this has given you a quick overview of the process involved in creating a toolpath. Next time, we'll learn how to move lead-ins and add bridges to our toolpath.